All right, this unit is entitled work and energy, and we haven't talked about work at all. So if we think about, let's say, an object that happens to be moving on a surface, let's say it's going at a velocity of 2 meters per second. Let's call this a 3 kilogram object. So if we have a 3 kilogram object moving at 2 meters per second, and we want it to speed up. Now the way we would actually get this to speed up is to apply some sort of force. So let's do a 6 Newton force acting on this. That would get this object to increase its velocity very quickly. And let's say that, this happens over a certain amount of distance. Let's say it happens over a distance of 5 meters. We know that this thing will be traveling faster than 2 meters per second as it continues to move to the right. Now here's the thing, it didn't lose any potential energy. This thing is on level ground the entire time. So by applying a force over a distance, what we're doing is we're adding energy to the system. Now let's look at this from an old perspective. If we have a 6 Newton force on a 3 kilogram object, that's pretty easy to see if you use Newton's second law, that the acceleration would end up being 2 meters per second squared. And we're doing this over a distance of 5 meters, and our initial velocity is 2 meters per second. So we can actually figure out what VF is using kinematics. Probably want to go with our time independent formula here. So when we look at this formula here, we have this as 2 squared, A is 2 meters per second squared based off of our calculation, and then delta x is 5 here. So running through the math there, we got 2 squared plus 2 times 2 times 5. That gives me 24. I'm going to square root. And then what I can see here is that my final velocity ends up being, if I round it, 4.9 meters per second. So I've clearly gained some kinetic energy here. And we've done it by the application of a force over a distance. So this is where we get into the idea of work. There has been work done here. And what work has done in this case is it's added energy to the system. And the type of energy that was added was kinetic energy. So essentially, we want to define work a certain way. Work allows us to add or remove energy from, we'll call it an object or a system. A system is a very technical term right now. From a system, and then this is done by applying a force over some sort of distance or displacement. I'll go with displacement. So, formula-wise, the way that works out is this. Work is equal to F times D times cosine theta. I see some textbooks use delta X as well, which would be perfectly legitimate. In fact, we're very used to using delta X. So if you choose to, you could write it as F delta X cosine theta as well. It's entirely up to you. Now, right now, we have a force that way and a distance that way in our example there. And theta is the angle between F and D. So right now we have no angle between F and D, and cosine 0 is 1. So another way of looking at this is you may have a force that happens to be not parallel to your displacement vector, something like this. In that case, then you would have that angle theta come into play. And what we want to recognize is that we could break that down into a parallel component that would be F parallel, and then you'd have a perpendicular component, F perpendicular. It's the parallel component that does work. The perpendicular component actually does no work. So if you looked at these individually, that would be an angle of 0, and cosine of 0 is 1. That would be an angle of 90 with respect to D, and cosine 90 is 0. So this component does no work. It's always the parallel component here. So we could actually rewrite work as F parallel D or F parallel delta X if you want to, but the parallel component would always be given by f cosine theta. So you can use this or this, and it's stating the exact same thing. You can either be in components, or you could just work with the formula itself. It's entirely up to you. It's important to note that f and d don't always point in the same direction if they're parallel. We'll get into that after. But if we go back to this now, what I could do is I could actually think about the energy and what's happening here. Now, there's no changes in potential energy in this scenario. Everything's on a level surface. So we're not even going to think about gravitational potential energy here. So what I would say is if we're trying to use conservation of energy here, we're going to say that we start out with a certain amount of kinetic energy. But what we do is we put in work. That changes the energy of the system. And by doing that, in this case we've added energy, we now have a different kinetic energy. So an expression like this is typically called the work energy theorem. And very easy to do, because if you look here, I know what my starting kinetic energy is. It's 1/2 mvi squared. My work has to have been the force times the distance times cosine theta in this case. And then my final kinetic energy would be 1/2 mvf squared. So looking at all these things here, basically I could go 1/2, the mass is 3, the initial velocity is 2, we square it. Our force is 6, our distance is 5, and cosine theta ends up being 1, right? And then we have 1/2 times 2 here, and vf squared. And what we could do is we can, excuse me, not 2, it's a mass of 3, times 1/2 times 3 times vf squared. We can run through the numbers here, see how it works. So putting in these numbers here, 1/2 times 3 times 2 squared plus 6 times 5 equals 1/2 times 3 times an unknown squared. And what do I get? When I solve for VF, I get the exact same answer, 4.9 meters per second squared. So we can figure out how fast it's going the old-fashioned way, like we did up here, or we could do it from an energy perspective like we've done down here.